Hey everyone, welcome to Leetcode Weekly Contest 286. Wish me luck. Make sure to subscribe if you haven't already, and let's go. Right. Hopefully no rate limited. I haven't seen that in a while actually. Just copy paste that. I'm Dave. I see. Oh, interesting. Okay. And this seems like a greedy question. Range. Else if select I well, oh, it's number of deletions. AC. Interesting. Okay. Okay, so there's two cases. One of the cases is when the interlink is odd. In this case, then, is it 1 indexed? 9 times 10 to the power. So n is the number of digits. I have to decide. 10 to the n. If 9 by 10 to the n is greater than I, then stop append -1. Otherwise, I don't think I need to separate the cases. I think I can do that. from 10 to 1 plus y. I don't know if that's correct. Nope, it is not. Probably should be the other way around. Submit that. AC. Okay. Have I solved this problem on binarysearch.com? I think I might have. Is it that one? Okay, so I was too slow code. I'm gonna go cheat. No, that's too slow as well. Yeah, so that's too slow. About this one. Yeah, that's the wrong time complexity. Yeah, that's the wrong complexity. Okay, I need to think about this more. Surely there's not like a segment tree or something. I feel like that would time out. I think it's probably this constraint that makes it all right. Okay. Exactly K. Oh, I didn't see that. Okay. So if the pile is less than 0, k equals 0, return 0. Otherwise, we're gonna return negative infinity. Oh. Pile. I. Okay, in this problem, I would have actually benefited by thinking about it less, I think. Am I looping over things correctly? So if remainder is less than 0, I'm going to return negative int as well. Oh, that should be a remainder. Okay. No, this is a very slow solve. Yeah, that was very slow. I overcomplicated that one because I thought it was going to be harder than it actually was. I mean, no one has finished, like, it hasn't updated yet, but I guess I'll go through the solutions. I shouldn't have taken so long with that last question. Yeah, that was just not a good solve for me. I thought it was going to be hard, but then it wasn't hard. I actually reckon if I copy-pasted my solution from binary search, it actually would have been better. This might have worked directly, I think. Actually, let's check. I want to know if I should have just copy-pasted from directly for my binary search submission. No. All right, so I should have copy-pasted from binary search because that would have been an insta-solve, pretty much. Yeah, I should have done that. Oh well, I'm a bit regretful. I'll go through the solutions. So all I'm doing is first I'm removing duplicates by converting them to a set. Then I'm just directly brute forcing for each element in A. That's in the first list. For each element in the first list, if it's not in the second list, I'll append it to the answer, and I'll do the same for the other one. So this is direct. It's pretty simple because checking the element in a set is done in O one time. The total complexity of this is just O nums1 length plus nums2 length. So even though they're 1000, you could have brute forced it and made a worse complexity, but this is good enough. In this one, this is a greedy problem. Basically, the main idea is in this array, we should always choose this element as the first element. And that's because there's really no reason not to choose this one as a first element. We can prove, if we want to do this more formally, I think we can prove it by contradiction. So we can prove that there always exists an optimal solution keeping nums 0. As a contradiction, let's say that no optimal solution keeping nums 0 exists. Then let's say that the first pair in the leftover array. So when we're trying to minimize the number of deletions, we're trying to maximize the number of elements that we keep. So I'm trying to show that this first element of nums, we can always keep that one, as long as there is at least one pair left over. As a proof by contradiction, let's say that every optimal solution deletes the first element. Then let's say that the first pair in our resulting array is nums I and nums j, where 0 is less than I is less than j. Then we have either nums I or nums j is different to nums 0. If nums j was different to nums 0, then I could have replaced nums I with nums 0. And if nums if nums 0 is not equal to nums j, I could have taken nums 0 and nums j as the first pair instead. And if nums 0 is not equal to nums I, then I could have taken nums 0 and nums I as the first pair instead. And because nums I and nums j are not equal, at least one of these conditions is going to be true, which means that in either case, there will be an optimal solution where I replace one of these numbers with nums 0, and that completes the proof by contradiction. Therefore, we are always going to keep this first element left over. So if we're keeping this first element left over, we simply find the first element which is not equal to that element. Like if, for example, I'd scan this until I find the first element which is not equal to 1, which is this 2. Then once I find this 2, that's the one pair in my resulting array that I'm going to keep. And then I keep doing the same on the rest of the list. So my implementation is L is like, so when I say pair, I mean that in the resulting list, let's say I end up with 3, 4, 6, 8. I mean that I'm having 3 and 4 as a pair and 6 and 8 as a pair, just in case that was confusing. Now, L, when I iterate through my list, L will represent the first element of the current pair which I'm building. So and then L equals none will represent that I just finished making a pair and I don't have this first element of the next pair. So basically, if I scan through a list like this, for example, when I've processed this 3, I'm going to put this 3 as the beginning of this pair, but I don't know what's the second element of the pair yet. When I see this 3 can't be in the same pair as this 3 because they're equal, so I ignore this 3. When I see this 4, that means I can take this 4, so I'm going to put this 4 in this pair. Then I'm going to start building a new pair. When I get to the 6, the new pair doesn't have any elements, so I'm going to put the 6 there. When I see this 6, it's the same as this 6, so I can't take it. When I see this 8, I'll put it in that pair. So that's all my algorithm simulating. L equals none means that I'm waiting to build a new pair, and if L is not equal to none, that means that's the first element in the current pair I'm building. So if this current element, if I'm building a new pair, I'm going to set the first element to that number, and if my pair is if I currently have one element in the pair, I'm looking to complete it, and that first element is not equal to my current element, that means that I can put that number in my pair. So ants here are my variable ants. It's just the that's just the number of elements which I'm going to keep, and then the answer is just the total number of elements minus the number of elements I keep. Somehow still getting 4th place, even though that was a terrible solve. I don't understand how, but I'll take it. Okay, in this question, I really should have copy-pasted from binary search. That would have been like a 7-minute solve. Oh well. Oh, this is already from the merged leaderboard, because that's Leetcode China. Which means I'm actually getting 3rd place in the US side. Okay. What was I going to say? Okay, for this question, first we need to handle the palindrome part. How do we check if a digit is a palindrome? Well, let's say, for example, we're going to build palindromes with 4 digits. Now we can see that if we have 4 digits in our number, but we can see that only the first 2 digits actually matter. So if my first 2 digits are AB, then we already know what the 3rd and the 4th digits have to be, which is ABBA. And then if I have a palindrome with 5 digits, the only digits that matter are the first 3, because then I can figure out the last 2 digits. So first, let's try to ask how many palindromes are there with X digits? Oh, caps lock. First, let's consider X is even. Let's just say X equals 2K. So there's 2K digits. That means that only the first K digits actually matter. Well, we can see that basically pretty much any combination of these first K digits will just give us a unique palindrome. So each of these digits has 10 different options. And that means that there will be 10 to the K combinations to choose the first K digits. However, the palindrome can't start with 0, which means that the first digit, instead of having 10 options, it actually only has 9 options. So actually the number of palindromes of length 2K is 9 times 10 to the power of K take 1. And if X is odd and X equals 2K take 1, the same thing applies, because we need to find K digits, and the first one has to be not equal to 0, and the others can be any of the 10 other options. So in my code, instead of calling it K, I called it N for some reason. I called it N here. So first I'm checking if the number of possible palindromes is less than my current query, then the answer is going to be -1. Otherwise, let's work through an example. Let's say I'm going to have I have int length being 4, and I need to find the 20th palindrome. Well, if we consider, since we don't care about the second half, we can pretty much just concentrate on the first half. We need to find the 20th 2-digit number that doesn't start with a 0. So we can see that if we start counting, if we start finding the palindromes of the first 2 digits, so finding the combinations of the first 2 digits, the first combination is 10, the next one's 11, then 12, then 13. And we can see that this is just going to keep counting up until we get that the 20th palindrome is 29. And that means that our palindrome must be 2992. More generally, if we have, let's say we had int length equals to 5, and we needed the 150th palindrome, we need to find the first 3 digits. The first possible combination is 100, then the next one will be 101, and so on. This is just going to be an ascending sequence. And since it's just consecutive numbers, we can easily find the xth term of this sequence fast. I kind of just do a little bit of math. Basically, yeah, it's just the current I plus some power of 10 take 1. So the way I figured out this, I kind of just figured out that formula by trial and error, I guess. Not really. So I knew, for example, that the first palindrome of length 5 is 100, the second palindrome is 101, and I noticed that this difference is always going to be 99 between the number which palindrome it is and the actual number of the palindrome. That's always 99. And if I was to do this one with int length of 4, the difference would be 9. And if I was to do one with an int length of 7, the difference would be 999. That's why I'm doing 10 to the power of k, take 1. That's the difference. And then I'm just going to add on the number I want. So that gives me f being the first half of the digits. Then if the length is odd, I'll simply take the first digits, then I'll take all of the digits up to the last one, reverse them, and put them on the second half. And if the int length was even, I'll simply reverse all the digits and put that on the back and concatenate that as well. Then I'll return my answer. So that's it. Finally, there's this question which I'm very sad about because I actually had code which did this already. So I should have copy pasted, but I doubted the complexity. I wasn't sure if my solution was gonna work. Is this the correct code? I can't remember what my correct code was. Okay. So let's pretty much our DP state is which pile. This is basically like a knapsack question, basically. So my question might be out of all the piles indexed up to pile, and I have remaining coins left. What's the maximum total? So basically what I mean is, let's take this diagram. If I was to find if pile equals 1 and remainder equals 2, that means that I'm considering all the piles indexed up to 1. So I will be considering the 0th pile and the first pile, and I have one, and I need to take 2 coins from those piles. If pile was 3, that means I'm considering the 0th pile, the first pile, the second pile, and the third pile, and then I would need to take 2 coins from them. So the basic, this is pretty simple actually. If the remaining number of coins I have left is negative, that means I did something wrong and I should return negative infinity as an answer. If I've run out of piles, then I should return 0 if I don't have any coins left to take, and I should return negative infinity otherwise. This is to ensure that I'm choosing exactly k coins. That means that I only return 0 if I have exactly 0 coins left over. That's what happens when I've run out of piles. Then there's only a few possibilities for the current pile. Either I don't take any coins from this pile, which means I'll transition from the previous pile number with the same number of coins left over, or I do take some coins from the pile, and I can just brute force for each element for each position in this pile. If I was to take all of the coins from that position upwards, and only those coins from that pile, what's the maximum answer I can get? So current will represent the value of the coins from the current pile which I'm choosing, and then for each possible choice of coins from my current pile, I will take the maximum of my current answer with the value of those coins plus my DP with the remaining number of coins to choose and with one less pile. And then this is pretty much very similar to knapsack, and yeah, that's basically it. Now, the reason why I was confused is a little bit because of the complexity. Let's analyze the complexity. Well, how many states are there? We have the number of states. That's just the total number of piles, n, times the remaining number of coins, k. Now, what's the complexity of the transition? Well, because we have this loop, this loops with the number. The transition is just the length of the current pile, which can be up to 2000. So in my head, I was thinking, therefore the total complexity is n by k by 2000, which 1000 by 2000 by 2000, that's too big. So that's why I didn't think it was going to work. Now, actually, it turns out because of the sum, there's this condition which I missed. I didn't read it properly. The condition is that the total number of coins is at most 2000. And that means that this is actually not the complexity. The actual complexity is, well, I haven't quite worked it out, but I guess I'll work it out now. Pretty much, let's consider for any pile, instead of finding the transitions for a particular DP state, I am going to think about it a different way. I'm going to think for each pile, out of all DP states and transitions that involve this pile, how many operations or calculations or checks do I do? So for any particular pile, the number of times that this loop executes, well, that's going to execute the length of this pile times, and there will be remainders. There will be up to k states that involve this pile, k states because of this remainder state, and for each of those k states, for this current pile, this DP thing will run in proportional to the length of the pile. So for any pile, the complexity is the length of the pile times k, and that means that the total complexity, if I sum this value up for all piles, that's just going to be k times the length of pile 0 plus k times the length of pile 1, and so on and so forth. And I can see that if I factor k out of that, that's just going to be k times the length of pile 0 plus the length of pile 1, and so on. But I'm actually guaranteed that the sum of the lengths of piles is at most 2000. So in total, that's just k times 2000. And technically, it's more like k times 2000 plus n, but that's also fine. And yeah, that's basically why this still has good complexity, even though it's less obvious. It's the same reason why if you do it like a DP on some directed acyclic graph, even though one vertice might have many outgoing edges in your DP, overall the complexity will still be good if it's proportional to the length of the degree and there's few edges in the graph. Anyway, I don't know how I still got, okay, 4th place. So this person's from China, which means that they don't count towards the prize. So I actually got 3rd place, which is the backpack. So that's, I guess it's just another backpack. So that should be good for my rating as well. My current rating is 3309, which means I'm getting close to top 10. Anyway, thanks for watching. See you guys next time.